All right, folks, back at it. We're here for lecture number 2. I got the same shirt on, so you can tell it's not a different day. Just keeping this going. All right. Hope you're ready. I'm ready. Okay. Let's do it. Okay, so let's just pick up right where we left off, shall we? We're going to get into now molecular partition functions and more on this notion of populations or populations of state. And molecular partition functions are useful equations that actually allow us to calculate the population of a state. So we recall the Boltzmann distribution, and I'm going to just write it in a slightly different way than I did last time. So I'm going to write in I, so number of molecules in state I over in total, so over the total number of molecules. And so now I'm going to write that as exponential negative, and I'm going to write negative beta times EI. Okay, I'm actually going to make this pen a little bit thinner. There we go. Where beta is 1 divided by kBt. Okay, so you remember last time we said it was E raised to the negative energy divided by kBt. Okay, and there's definitely some exponential algebraic tricks at play here. Okay, and so that's my number of molecules in state I. And if I want to divide this by the total number of molecules, then I'm going to say that's the sum of all of these exponential contributions, okay, where now I'm going to say that's beta times capital E. And here in this case, if I take, the sum of all populations I times their respective energies, that's going to give me the total energy E. Okay? And of course, right, the sum of all populations of NI will equal in total. All right? So you can see that this is really still the same Boltzmann equation we wrote last time. It's just slightly different and using a little bit of algebra as a matter of convenience. Okay, so now I'm going to write here the molecular partition function, which is going to be based off of this Boltzmann distribution. Okay, and I'm going to write that as little p sub I. And so this p of I is the fractional population of state I. So it's basically the same thing as this, right? Like so, or really you could think of them as a decimal percentage, if you will, not a fractional, okay? And I'm going to say that equals exp bracket negative beta times energy, and I'm going to say divided by Q, okay? Where Q is my actual partition function. All right, Q is the partition function. And so that Q equals the sum of all of those states, of course, raised to this exponential equation. Okay? So if the states have the same degeneracy, and so notice over here a degenerate state, 2 or more states having the same energy level. So think of a p orbital, for example. And so I'll give you, so in that example, right, if I have like the, let's say the 2p energy level, we really recognize it goes 1, 2, 3. So that's got 3 equivalent degenerate states. Or like a d orbital has 5, or an f orbital has 7. Okay? So that's what we mean by degeneracy. So if there are equivalent degenerate states, I'm going to write that as Q equals the sum, and I'm going to just write a different letter here to signify it's just slightly different, capital I. So I'm going to say now that's G sub I, Q and G, okay? So that the G is my degeneracy term, and then of course that's still going to be times this exponential, okay? So basically, if there are degenerate terms, let's see, degeneracy, then we can account for those degenerate terms when we're summing up this total population, okay? So we're not really going to get into the nitty-gritty details of degeneracy really until like 362 with spectroscopy, but it's a good time to introduce this concept, okay? So now let's apply this partition function to one of our energy levels, okay? So let's consider a system with linearly spaced energy levels, and that turns out to be the vibrational modes of energy have linear spaced energy levels. And I'm labeling those as 0, E2, E3, E4, E, which you could still think of as like level 1, level 2, level 3, level 4, level 5, etc. But now I'm putting values for their energy, okay? And so this ground state, I'm giving it a 0 value, which is not to say that it doesn't have any energy at that state. It has its base thermal energy given to us by 298 Kelvin, the kinetic energy available. But to go to the next energy level, it has to be supplied the value of E, right? So I can go from 0 to E, E to 2E, E to 3E, right? And they're all spaced by levels of E, okay? So we could think of these also, this 0 right here, as the vibrational number, which as it turns out also gets a Greek letter nu. So don't let that confuse you. There's too many Greek letters, or not enough Greek letters rather. So I will say that the energy of any of these states I is going to be given by this vibrational quantum number 0. And really I screwed this up. I should have said this is 0. And actually I think, look at this. Do I have an eraser? Oh yeah. I told you I'm learning as I go here, folks, on how to do this new technology. Okay, so really I'm going to give that a 0 to make this more correct for vibrational energy levels. Okay, so I'm going to say then any of those energy levels equals nu I, which is this letter here, and really this, yes, okay, now we're cooking. This is this value that I'm working on right here. Haha, all right. So now I'm going to say this is times then E, right? So E, 2E, 3E, 4E has that value, right? Depending on which level we're talking about. So for example, if I wrote E1, that would be quantum number 1 times E, okay? Or E2 would be 2E, okay, etc. So now let's build up the partition function for this system. So I'll start by writing Q equals. And we know our partition functions have this form. Let me just back up one slide. It has this form, this exponential to the negative beta times this value of E, right? So if I move forward here, so the first one that I want to sum up is this level 0, which is going to be E raised to the 0 power, right? 0 times E. And anything raised to the 0 power is 1. So the very first term in my partition function is numero uno 1, okay? Because it ended up being E raised to the 0 power. So now the next term, okay, is going to be, and I just for convenience, I'm going to switch to writing that because it's not too bad. So E to the negative beta, and then it's going to be this value of 1 times this value of E. So I'm just going to write that as E right there, okay? Plus, and then my second term is going to be E to the negative 2 beta E, plus the third term is E to the negative 3 beta E, and so on and so forth, right? We can see that that's how we're carrying out that sum. We're summing it through all of those states in the partition function. So those of you that are good at math will recognize this as a Maclaurin series expansion. Maybe you did, maybe you didn't. Hopefully you did. But it's been a long summer, right? So I'll forgive you if you didn't recognize that right away. Okay, so in this Maclaurin series expansion, I can write this in a simpler way. I can write this as Q, the partition function, is 1 divided by 1 minus e to the negative beta e, right there. Okay? And so this would be a partition function for a system with linearly spaced energy levels. So for the electronic levels or the rotational levels, we should not expect this form of the partition function because it doesn't have evenly spaced energy levels. And this is really the only partition function I'm going to play with in this class. When we get into 362, we'll get much more in depth with all of those other partition functions. So as I said in the previous lecture, this is kind of like a crash course introduction to statistical mechanics. Okay, so now let's see. If we then go and expand this, suppose that I want to know the population of state I, any state I. Okay, so I remember I can write that as e to the negative beta, and I'm just going to put in this general term there. So we note that that can be connected to any one of these energy levels, right? Which is, of course, then divided by the total partition function Q, all right? And then now, if we consider that we're talking about a system that's linearly spaced, and we do a little bit of algebra, right? Plug this thing into Q, okay? And make substitutions, then what we get, okay, I'm not gonna show the steps explicitly, and anytime I skip some algebra steps, it's not my intent to, like, you know, make you memorize how to do the algebra unless I tell you I want you to be able to do this. So for now, I'm not too worried about it. I'm just gonna give you the result, okay? So when I simplify this, when I plug this in and make the simplifications, I can get the following, okay? I get 1 minus e to the negative beta e, big capital E, okay, times e to the negative beta, and then I'm going to use this little lowercase eta e. Because now what that's going to allow me to do is whatever state I want to know, if I want to know about the second, third, or fourth state, then I can plug that value into here. But this remains as e to the negative beta eta e. Okay, beta e, excuse me. All right? Okay, so now to actually make calculations with this, it's not as straightforward. We have to do a couple of extra steps. And so let's get into this. So we're going to use this example from vibrational spectroscopy, all right? So let's get into this whole beta thing. Remember, that's just a shortcut for saying 1 over K Boltzmann T, okay? Which is going to have units of 1 over energy. Remember, K Boltzmann is joule per Kelvin, times the Kelvin is 1 over joules, all right? And so the value of KBT at 298 Kelvin is, and I just did this directly, so make sure that you can get to this value yourselves, 4.116 times 10 to the minus 21 joules is the value of KBT at room temperature, okay? So 298K times 1.38 times 2 minus 23. So this is about 25 milli electron volts. So 0.0257 eV, so about 26 milli electron volts, right? 1, 2, 3. But if I want to do this example from vibrational spectroscopy, it becomes useful to use units of wave number. You guessed. Okay. And so remember from the first lecture, I can calculate wave number by saying 1 over the wavelength, but in this case, because I have energy, I can just simply say that it's energy divided by hc, okay? And that will give me this value of beta in terms of wave numbers. We can keep it in terms of energy, right? If you look at these equations, right, if I have, these values in joules, then my beta needs to be 1 over joules. But it's very useful as chemists, right, to be able to convert between units, okay? And I like the wave number and the electron volt a lot. So to make that conversion, okay, what I need to do is say K Boltzmann T, which remember the product KBT gives me energy, divided by HC. So when I say KBT divided by HC, it's going to give me that value in units of wave numbers. Technically, it's going to be 1 over meters, and then I have to convert. All right. So then I can take this value right here, the 4.116 times 10 to the minus 21 joules, and just divide it by Planck's constant times speed of light. I'm just going to leave those as H and C. Do it out for yourselves, right? Make those calculations happen. Pause the video if you have to. I'm just going to keep moving forward. So when I do that, I get 207.22 1 over meters, and in 1 meter, there's 100 centimeters, so I get 207, we'll just leave it at that, that's fine, 207 wave numbers is the value of K Boltzmann T at room temperature. Okay, that's a good thing to remember, because now what we can do with that, and so remember, technically, if the way I've done this, KBT equals HC, this equals 1 over beta. And you notice beta equals 1 over KBT. So technically, beta equals 1 divided by 207 wave number. And now what makes this useful is when I go up to this partition function, I can supply my value of energy in terms of wave numbers, which is really, really useful if we were to use FTIR data, right? If we were to use the stretching frequency of an OH bond, right, at about 3,500 wave number, we could plug that into our equation directly. Okay, so let's do that. Let's keep moving forward. And so here's a calculation to make. So calculate the population of molecule AB, generic molecule AB, right, and its ground vibrational state, nu is 0, and its first excited state, nu is 1, if it has a vibrational energy of 2,000 wave number. So that means like if we were looking at an infrared spectra, right? Let's see here. We have wave number on this axis, and we'll say percent transmittance on this axis, right? Then we would see like this peak, and that would correspond to our 2,000 wave number. Okay, so what is a population of states? So here I've drawn up the molecular partition function that we just discussed. All right, and my nomenclature is should be somewhat consistent. Okay, so we're gonna go ahead and calculate this thing. So once again, as always, you can pause the video, try the calculation out for yourself. You can watch me run through this while I'm listening to some music. Hopefully they don't flag me for copyright infringement on the YouTubes. So let's go for it. Let's calculate this sucker. Okay. Okay.
believer. I ain't lost and this ain't shipwrecked. I feel small in this big wide world, and mommy ain't said, honey, I shrunk the kids yet. I ain't Jesus, but I'm walking on water. There's no bombs here, there's no walkers. I can break out of jail with a lighter. So is there any point in making laws, blood? This ain't Atlantis, are you sure? I nearly suffocated when I touched the shore. No rain, condoms get poured on up the road. You'll never guess who I saw. It's K8, look, skip on the beat like Ollie in the gym. Honeycomb home, this is where I wanna live. Just found it like Nemo. On a kilo, I know the whip is greener, but it's green though. On the other side of the fence, bind to the ends. Look, no fence, no stress, no rent, no superficial shit, this real flow. Where the women look up when the beach goes, and the speech goes like, hi, little lady. 6 on the beach, wanna try for a baby. Word in the village, I'm a little bit crazy. Swagger on 100 degrees, no A. Look, if heaven had a VIP, this is it, white sand, blue sea. But I don't know who they are, and I'm damn sure they don't know me. But I come in peace. Cool, white flag. No war, no guns, no war. Just life, just love, no time, just fun, no time. Just me and my mind, just me and my wife. But tell me if I'm dreaming, cause I don't wanna wake up till the evening. I don't wanna be left sleeping from all the diseases that I breathe in. Look, respect the island, no stealing. And don't bring religion here, no free kings. Integrating them, we ain't leaving. We come on a peace sing. White flag, white flag.
Okay. Okay, so let's walk through what I did here. So a lot of this is kind of plugging and chugging and recognizing what to do with these, quantum numbers. Remember I told you the ground vibrational state is nu 0. First excited state is nu 1. And you notice in this first term, we don't have any of that, right? It's just going to be, remember, beta is 1 over the 207 wave number. And we said the energy is 2000 wave number. So you can see by having equivalent units, it makes life much easier. All right. And this second chunk, because for the ground state, nu is 0, this becomes an e raised to the 0 power, which is just 1. So here we get 0.99936. And if you remember from the lecture, the first lecture, we said nearly everything will be in the ground vibrational state. And here you can see we now have the quantitative proof of that, right? 99.9936% of the molecules with this 2000 wave number energy are in the ground state. And now it's tempting to say, well, then wouldn't the population of the next excited state be 1 minus this quantity? And it, for the most part, is. However, we still have to accept the fact that there could be populations of molecules in state 3 and 4 and 5 and 6 and so on. So when we go to make that calculation population of level 1 as opposed to level 0, we still have this term here in the partition function, which is comes out to be the same result. But now it's e raised to the 1 times beta times e. Okay? And so that makes it just slightly a little bit different. Oh, I wrote 2, 5. I meant to write 2, 3. Right? So it makes it just slightly different than if we had done 1 minus this value. But all the same, a fraction of a fraction of a fraction of a percent of these molecules are in the second vibrational excited state. Okay, so we've just quantitatively proven what we learned from the equipartition theorem last time, and that's the game we're going to play in PChem. We're going to talk about concepts. We're going to try to wrap our head around these concepts and make guesses, and then we're going to calculate that to prove if it's correct or not, or reasonable. Okay, so let's move on. We have a whole bunch of these partition functions that I could draw up, and I'm just going to write what the partition functions are and not ask you to memorize them or anything like that, but they do look very similar. Okay, so for the electronic, all right, the partition function for the electronic goes as the sum over all quantum number n, principal quantum number, times the degeneracy, and I'm going to use this letter J here for another letter, and that's e raised to the negative beta e sub j. So it looks very similar, right? And there is a degeneracy term for the electronic levels, as we talked about, right, with p orbitals and d orbitals and f orbitals. Those exhibit degeneracy, equivalent energy states. So the vibration, we just did that. So I'll write it again, Q of V, Q for vibration, okay? And that's going to be the sum of all vibrational numbers. And that's going to be no degeneracy terms here, but now that's e to the negative beta. Also, and times eta sub nu. So a very similar form. Okay. Our rotational levels look like this, QR, and that's the sum over, this is capital J, which is the rotational quantum number, and we'll get into that in 362. This is my degeneracy term for rotational. It goes 2J plus 1 is like this whole value of G, but still it goes E. What do you want to guess? To the negative beta. Right? They're all like the same form of the equation. It's really just a matter of how you calculate the value of energy for those levels. And the only one that's different is the translations, and that goes as V for volume, the volume of the system you're talking about, and this parameter lambda cubed, where lambda is what's called the thermal wavelength, okay, and the thermal wavelength goes as h, Planck's constant, all divided by 2 pi m k Boltzmann t. Okay, so again, we're not going to do much with these other partition functions, but we can use them in a very similar way. And if we want to know information about our total state here, okay, so let's see, how can we write this up? So my total partition function is going to be a product out of all of these. So QR times QT times QV times QE. So we can talk about a total molecular partition function, which is going to give us the population of every single one of these states. It gives us the full picture of the molecule, okay? And of course, the total energy of that system is going to go like, the energy of the translations plus the energy of the rotations plus the energy of the vibrations plus the energy of the electronic transitions. So those energies are additive. The populations are multiplicative, okay? So keep that in mind. This is a good conceptual detail to know, all right? So now, moving forward. So this is where we're going to kind of get into a rather big derivation. And I think that I'm going to turn this derivation of the Maxwell-Boltzmann distribution. So this is going to give us the population of states of translations specifically. I'm going to do this in a third video, okay, because this will be quite a lengthy derivation. So I think that's a pretty good place to stop for now. And, expect one more short lecture video for this week, and that'll wrap it up for week 1 on what I'm calling fundamentals. Before we even get into the thermodynamic world, we have to know some fundamentals about the statistical mechanics world. All right, folks. See you later.